Here we are considering uniform linear motion. The uniform part of uniform linear motion. Uniform means the same. In this case, the thing that is the same is a constant velocity. Uniform linear motion is an object moving with constant velocity. And so we can say that the particle is moving with this constant velocity for a duration of a time interval delta t, and during that time, it undergoes a displacement delta x. So at t initial, at some initial time, it's at some initial position, some location on the x-axis. The particle has a velocity at that time. As time elapses, the particle moves. It's moving with constant velocity and zero acceleration. Acceleration is the rate of change of velocity. So if the velocity is constant, the velocity is not changing, and the acceleration is zero. As time passes, the object undergoes a displacement, and at the end of the interval, our particle is over here at t final. Our particle is at some new position, having undergone a displacement delta x. Delta t is our final time. We could say here that t final would be t initial, the initial time, plus however much time elapsed while the particle is in motion. And the particle's velocity is still the same as it was before, because the velocity is constant. So the quantities that we have to consider here is the velocity. Again, there's only one velocity to consider because it's constant. And then there's the displacement, how far the particle moves and in what direction, and the elapsed time. The acceleration, in this case, is zero. That's part of the assumption of the uniform linear motion. We would build from this definition that the velocity is the derivative of the position, and from that we can derive equations that can model and describe the motion. This would be the model of uniform linear motion, and then these would be the equations that would describe that motion. So if we have motion with a constant velocity, that's what uniform linear motion means, is a constant velocity. That means that our Vx is constant. If you have a constant function, a constant value, that is a horizontal line. So you're going to be seeing this a whole lot in various circumstances. When you have a constant value that you are graphing, that constant value gives you a horizontal line when you try to plot that. With velocity being constant, remember that velocity is a vector quantity. There's two parts to that. There's a magnitude and a direction. And so the magnitude part is the speed. It's moving with constant speed. And the direction, in this case, it's moving in a straight line. It's moving in one direction along that line. The velocity is the derivative of position. That is the slope of the tangent line is your derivative. So if our velocity is constant, then that means the slope of our tangent line is constant, and a curve with a constant slope is a straight line. That is a linear function. Our position graph, our position as a function of time, is a linear function. It's going to look like this. Here it is linear, with the slope being the constant velocity that we have. We're able to take this definition of velocity being the derivative of position, and we can find a couple different equations to describe this uniform linear motion. The first of which is to say that delta x, our displacement, is our velocity times delta t, the elapsed time. That's basically taking this derivative and extending it out over a finite interval. We're also able to solve this equation for x, for position. Basically, if velocity is the derivative of position, then position would be the time integral of velocity, but you need an initial condition. You need to have a delta t, a initial t and an initial x, a initial time when we're starting our clock, when we're starting our measurements, and an initial position where we are when we start that clock. We need to know what our velocity is, and if we know where we were at the beginning and what direction, how fast we're going, we can figure out where we're going to be in the future. Notice that this equation here looks a lot like y equals mx plus b, which is basically our straight line that we have here. So we made the argument that that's the behavior it has to be. Solving this out with our initial conditions gives us an equation that looks just like that. In another lesson, we'll see these full derivations, but these are your birdie notes. These are what you should have memorized. And then our displacement, our distance traveled, and the direction that we traveled in is typically measured in meters or feet. Those are our 2 units in our 2 unit systems. Time is always measured in seconds. Velocity is in meters per second or feet per second. These are derived units. They are a rate of change that are derived from meters, and feet and seconds are all base units. So these are some of the first derived units that we'll see.